Now, we will derive MLE for Gaussian models. Here are the typical steps for MLE. First, we draw independent training data from the unknown data distribution. We choose a model, in this case a Gaussian distribution, with learnable parameters being the mean, mu, and the variance, sigma squared. We define the loss function as the average of the negative log probability for every data point. We choose the parameter that minimizes this loss function. To derive the MLE, let's start from the Gaussian probability density function. This is the log density, and we can further write it in this way. Use this expression for the loss function. We can rewrite the loss function and ignore the last term because it is a constant. To minimize this loss, we calculate its derivative with respect to mu and set the derivative to 0. So the optimal parameter mu that minimizes this loss is simply the sample mean. Similarly, we can calculate the derivative of the loss with respect to the sigma and set the derivative to 0. The optimal parameter sigma squared is simply the sample variance. This figure visualizes what the maximum likelihood estimation looks like for the Gaussian model. On the left, we have a histogram of the data and several Gaussian curves with different mu and sigma. Some curves clearly do not match the data well, while one curve matches the histogram much better. On the right, we plot the average negative log likelihood as a function of mu and sigma. This shows the loss landscape. It has a valley and its minimum occurs exactly at the MLE for the mu and the sigma, which correspond to the sample mean and the sample variance as we have derived. So we can think of MLE as searching over the parameter space and pick the point at the bottom of this loss landscape, which corresponding to the Gaussian distribution that best fit the data histogram.